All right, do we have any questions on precipitation reactions or balancing equations from last time? All right, let's get into acid-base reactions. We kind of started it already. Whoa. So the one we did last time was sodium hydroxide as an aqueous solution with hydrochloric acid, also aqueous.
It's not that. Is it supposed to be that?
Yeah, it was. Thank you. Good? All right. Okay, what type of reaction are acid-base reactions? Double replacement or double displacement, depending on how you want to say it. Okay. So let's practice this. Can you predict the products?
NaCl and H2O.
Yeah. We did this last time, right? So water is a liquid, and sodium chloride is aqueous. We good with that? All right. So before we do anything, maybe we should balance this. Is it balanced?
Yes.
Oh, okay, it's already there. Now let's write the net ionic equation. We only write net ionic equations for double replacement reactions. So for precipitation reactions and acid-base. So what's my product?
Don't we just write it down if we have
A solid?
a solid?
No, we write it down if we have a product. It's just water. The non-aqueous solution, the non-aqueous substance. So we just have water. And how do we get water? From here we take what part? The OH minus, and from here we take the H plus. This is always going to be the net ionic equation for an acid-base reaction, or for a neutralization reaction anyway. Good? This right here tells us it's the acid. This hydroxide tells us it's the base. And that's all that's happening. You throw this salt in water, it dissolves, dissociates, you get hydrogen ions and hydroxide ions. Good? All right, let's give you a better definition of an acid and a base. An acid is a proton donor. What does it mean to be a donor? To donate something, to give something away, right? So what do you think? Would an atom be able to donate a proton? Or a molecule be able to donate a proton? Seems like it would be a nuclear explosion, right? So what are we saying when we say proton? This is the hydrogen ion. Because if you think about a hydrogen atom, most hydrogen atoms have one proton, 0 neutrons, and 1 electron. If we rip that electron off and have it become an ion, what is it? A proton. That's all it is. Okay? A proton is just the hydrogen ion. Make sense? So anything that has hydrogen ions is an acid if it's an aqueous solution. If there's no water, there's no acid. Okay? And the base is the opposite of that. It is a proton acceptor. And again, it also has to be an aqueous solution. So that's still a hydrogen ion. If it takes the hydrogen ion, accepts it, that's the base. So does it have to be OH minus to be a base? No. What does it have to be? An anion. Has to have an anion in there that's going to accept that proton. Okay? Any questions on the definitions of acids and bases? Yeah, Michael.
How does base accept a proton? Or is that just accepting the hydrogen ion?
It's just accepting the hydrogen ion, which is a proton, right?
Yeah.
Yep, that's it. And so this only happens after it dissociated, right? Because it dissociates and then it picks up the hydrogen ion. Because it can't do that unless it's an ion form, right? Any other questions? Okay. Next, let's talk about how we tell if it's a strong acid or a weak acid. It's a strong acid if it dissociates completely. That means it has to be a soluble compound to dissociate completely, right? We talked about the solubility chart or the insolubility chart. So examples of strong acids are going to be HCl, HI, HBr. What's this called? HNO3? Nitric acid. What's that called? Hydrochloric acid, hydroiodic acid, hydrobromic acid, right? Okay. Also, if we have H2SO4, HClO4, yeah. What do these guys have in common?
H.
Sure, good. They're all acids. Good. What else? What makes these strong? These guys are all on the solubility chart. These are soluble ions. Hydrogen is also a soluble ion, but if we have HF, fluorine's not on our solubility chart. It only slightly dissociates, so we call it a what? A weak acid. If it dissociates slightly, or if it slightly dissociates. And if it doesn't dissociate at all, it's not an acid, or a base for that matter. So some examples here. H3PO4, because phosphate is in our insoluble chart, right? Doesn't mean it's fully insoluble. Another one, is HCO3, H2CO3, carbonic acid, HF, hydrofluoric acid. And this one right here kind of goes against our solubility chart. CH3COOH. Anybody know what that is? Acetic acid. Okay. Well, we put the H right here. Why do we? Why do we put it on the right side instead of the front? Because don't we normally put the cation in front? It's because this is the way that it's structured, and that hydrogen has to be bonded to the oxygen. That's why. Can I write it this way? HC2H3O2? Sure. Still acetic acid. But this is generally how it's written, as an acid. And these guys, insoluble, insoluble, slightly soluble. These are all, and this one right here just kind of goes a little bit against that, because that one's always soluble, right? Turns out we still call that a weak acid. Just think of, what's another name for acetic acid? Vinegar. That's kind of a weak acid. Any questions? How do you determine if it's a strong acid or a weak acid? Slightly dissociates, it's a weak acid.
So vinegar only slightly dissociates in water?
It's a great question. Doesn't seem like it according to our chart, right?
Right.
So that's an exception. It's not a strong acid. Still a weak acid.
Okay.
Okay? We could do the exact same thing with bases. How do you tell if it's a strong base? If it completely dissociates, same thing. Now, hydroxide is on our insoluble chart, right? That means it has to be hooked up with what? Our soluble cations. So examples would be NaOH, LiOH, any group 1 ion with hydroxide, okay? Potassium hydroxide and so on. Barium hydroxide, because this is the exception for hydroxide. Hydroxide is insoluble unless it's with barium, strontium, and calcium, right? And then, of course, NH4OH, ammonium hydroxide. And they're strong because they're with either a always soluble ion or one that goes, one of the exceptions. Just making sense according to our solubility chart? So that's another thing you just have to get down is which ions are soluble, which are not. Weak base, if it slightly dissociates. And examples of this would be any other ion, any anion, anions that dissolve in water. And I'm not talking about just the anion, but an ionic compound with an anion that will be dissolved in water. So for example, sodium chloride. That's a weak base. Salt. This compound dissociates in water, and that chlorine can accept that hydrogen ion, can accept that proton. That makes sense? But it's not a strong base. Strong bases are the ones with hydroxide in it. And there's another weak base that you need to know that doesn't really fit into any of that stuff. It's ammonia, NH3. It's not an ionic compound, doesn't have an anion, but it's still a weak base. How are we feeling? So what do you got to have down to really understand this stuff? The solubility charts. Okay. There are a few little exceptions, like acetic acid is a weak acid, and ammonia is not even an anion, but it's a weak base. What about iron hydroxide? That a strong acid?
Iron hydroxide.
Look at your chart. Has hydroxide. Does that mean it's a strong base?
Yes.
Look at your chart. Hydroxides are insoluble. So why are these strong bases? Because it's with a soluble cation. That's why. So don't just say, oh, if it has hydroxide, it's a strong base. Okay? Has to be with an always soluble ion, or one of the exceptions for hydroxide. Okay? We good? Okay, let's do one more example of a neutralization reaction. And what's a neutralization reaction? It's where we have a strong acid mixed with a strong base, and it completely neutralizes to make salt and water. That's it. Strong acid reacts with a strong base, producing salt and water. It neutralizes the acid, neutralizes the base, because an acid, as we found out yesterday or last time from experience, very corrosive material, right? Throw it on that aluminum, and it causes your teacher to cough and oof. Okay, whatever. So, salt and water.
You mean salt and water as in NaCl, not like,
No, it doesn't have to be NaCl.
it can just be
What-
any type of
Any salt, any ionic compound, yep. So the one we did up here, we dealt with NaCl and water, right? Specifically for that reaction. Let's do another one. So we got sulfuric acid, which is a strong acid, and potassium hydroxide, which is a strong base. What do we get? This is a double replacement reaction. KSO4 or K2SO4? Right? You gotta write it correctly. That's gonna be aqueous still. And water. So what's the net ionic equation? Should we balance this first? If we balance this, we have to put a 2 right there and a 2 right there. And then I think it's balanced. So if we write the net ionic equation, what's the only product we get here? H2O. So we have 2 H2O as a liquid. And how do we get that? 2 hydrogen ions and 2 hydroxide ions. Can we simplify this reaction? Yeah, they'll have a coefficient of 2, so just get rid of that coefficient. And it becomes H plus OH minus to H2O as a liquid. Again, this is always going to be the net ionic equation for a neutralization reaction. Questions? Am I going too fast? Giving you too much too quick? Yeah.
So it's K2SO4 because we like do the cross charges, and is that what gets us the coefficients of 2K? Because now we know.
Yeah, because we balance it.
Okay.
Because there's 2 potassiums right here, so we have to have 2 on this side as well.
Okay, and then that tells us.
But do you see why it's probably better just to balance it after you write the net ionic equation? Because if we did, then we wouldn't even have to worry about balancing this one. Follow? But either way, just make sure you simplify if you can. Anything else? All right. So we talked about precipitation reactions. Who can explain what a precipitation reaction is? Go ahead, Izan.
Aqueous solutions,
We have 2 ionic compounds in aqueous solution. Good. That's our reactants.
and then they form solid with
Yeah.
in aqueous solution.
Yeah. We form a solid plus some leftover stuff, right? Yeah. So you're going to form a solid from 2 aqueous solutions. Okay? Just like we saw in that demonstration last time with the 2 liquid solutions, 2 water solutions, and put them together and you got that yellow stuff, right? Okay. Doesn't have to be yellow. There's white precipitates, there's blue precipitates, just depending on what the reactants are. Okay. But I like that one because it's really vibrant and nice to look at, right? Okay. We good with precipitation reactions? Any questions on acid-base?
Precipitation reaction, it's a solid, and then what's the leftover stuff? It can be anything.
Well, it's going to be a soluble salt.
A soluble salt.
Okay.
Okay.
Yep. It'll be an aqueous component along with your solid. Because they just swap partners, and then one guy is gonna be insoluble, and the other substance is gonna be soluble.
And the insoluble is the solid thing.
That's right, and that's really our only product, right?
Yeah.
Because the other one is still dissociated in water.
And the other one called, the, what's it called? The spectator ion?
Oh yeah, yep, the others will be the spectator ions, good. So to write the net ionic equation for precipitation or acid base, you get rid of the spectator ions. Are we good with that? In fact, a test question will be, what are the spectator ions if these two compounds react? Do we need to do another example on that? How are you feeling? Yeah?
Yeah, let's do one.
Okay. So if we have, and I'll just give it to you like it'd be on the exam. If we have silver nitrate reacts with potassium chloride, for example, what are the spectator ions? So to do this, we just write it out. AgNO3 plus KCl, both of them are in aqueous solutions.
And how do we know if both of them are obvious?
Great question.
They tell us,
Because nitrate is always soluble, and potassium is a group 1 ion, it's always soluble. Yep. And if it tells you it's going to be in a precipitation reaction, it must be aqueous as the product, as the reactants, right? Okay. And this is a double replacement reaction, so somebody tell me the products, because you're going to have to be able to do this.
Isn't it, did you say it's always AD and then BC?
Maybe. For that general one, AD, yeah, B, CB, not BC.
is it the cation
But-
with the anion?
It's the cations swap partners. That's the easiest way to think of it. Or you can say the anion swap partners, either one.
So like AgCl and potassium.
AgCl, is that the correct formula?
Yeah.
Yeah, because this is a 1-to-1 ratio. So that's right. Plus KNO3. Is that the right formula? Yeah. So it's already balanced, good. All right. So which one is the solid component? AgCl. That one's the only one that's insoluble. Therefore, the spectator ions are what? That's a compound. K plus and NO3 minus. Those are the spectator ions. Does that make sense?
So just whatever isn't the solid.
That's right.
is the spectator
Then it's
ion.
going to split apart, and it's still going to be an aqueous solution because it's soluble. And those ions are the spectator ions.
Got it.
Good? Yeah.
So, I think I got it. I'm just trying to make sure I got it.
Good.
So it's like, cause, potassium a positive ion and then NO3 is a negative ion. And then silver, so is that like a covalent bond between silver and chlorine?
No, because it's a metal and a nonmetal.
Okay. So it's.
But why is it insoluble? Look at your solubility chart. Chloride is soluble unless it's with what? Silver, lead, or mercury. Right?
Oh,
Right,
So since that's the exception, that means it's a solid.
okay.
And I believe that these these charts, the solubility chart is on the reference sheet that I give you. Okay. And, oh, I want to say something before I forget. I'm still looking into it. Anybody take the midterm yet? Okay. I had one student take it, and she come and talked to me yesterday and says, I thought you said we can use the periodic table with the names on it. For some reason, I submitted the one with the names, and they changed it on me. And I called them and I says, hey, what's going on? Yeah, I think they said for 1210 it has to be the same one. So I am going to check with the guy who is in charge. I emailed him, I sent him a text. Anyway, he hasn't responded yet. And I'm going to see if I can get that, but sorry, if that's the case. But it's just for the midterm and the final. For the other tests, you could use whatever you have, right? But anyway, I'm going to push. And I asked him, I says, in the question, I says, I don't feel like this is important to have them memorize all the names to match the symbols, because we all have this other stuff to worry about. So hopefully he'll say, yeah, that's okay. And if he does, I'll have him change it. But just maybe plan for the worst and expect the best, right?
Will you let us know when you hear back?
Yes. Yep. All right. Any questions on double replacement reactions? You can make predictions on what the products will be. You're going to need to be able to do that and determine which is soluble or insoluble. Determine if it's an acid-base versus precipitation. Okay?
Can I ask a quick question?
And determine the spectator ions. Yeah.
Okay, so the very first example you gave today, the product was water.
Uh-huh.
How do you know that the product would be water? Just
Because the other one was
water
aqueous.
Okay.
And is that really a product?
No.
It's not. They're dissociated. They're not together. Yeah.
So are they spectator ions because they're not changing their phase? Like they're not.
Because they don't participate in the chemical reaction. So let's draw the complete ionic equation, just to show you what goes on, right? So this is aqueous. It's going to split apart into Ag plus and NO3 minus. Potassium chloride is also aqueous, so it's going to split apart, dissociate into this. This one is a solid, so it's not going to dissociate. And this one is aqueous because, well, has soluble ions, right? And so it's going to split into K plus and NO3 minus.
Oh, so because it stays
Yeah,
like.
nothing changes with that guy, with those ones. And what we're left with is the net ionic equation. So you don't have to write the complete ionic equation if it makes sense that which one the product is. But you can. You can write the complete ionic equation and find the ones that are the same on both sides. Those are the spectator ions. Get rid of them. And what you're left with is the net ionic equation. Good?
So the
Yeah.
spectator ions, the spectator, ions will be always obvious? Like the
Yes.
product?
So it's the ions that make up the aqueous product. Yep. So in this other reaction, this acid-base reaction we did, well, I guess we had one right here. Then we have potassium and sulfate are the spectator ions. Good? We good? Ready to move on? All right. Next, we're going to talk about oxidation reduction reactions. Okay. So I'm first going to show you why we call them oxidation reduction reactions. Originally, back long time ago when we first started doing chemistry, maybe, okay? Then we have something like iron with oxygen gas. And what do we get when iron reacts with oxygen? Anybody know? Rust.
Iron oxide.
Fe2O3. Okay, so this is a solid, this is a gas, this is a solid. Okay, and what do we say happens to iron besides it rusts?
It's oxidized.
It oxidizes, right? So iron is oxidized, and that tells us oxygen reduces iron to oxidize. So that's where the name oxidation reduction comes from. We'll talk about it more in depth in just a minute here. Okay? So what happens to iron? It started out to be neutral, right? And now it has a 3+ charge. So what happened to iron? According it lost electrons. It lost 3 electrons. So we say iron loses electrons. Therefore, we call anything that loses electrons, it is oxidized. Oxidized. And in this case, oxygen gains electrons because it started neutral and now it's -2. So we say that's reduction. Makes sense, right? Or reduced. Does that make sense in your brains? Doesn't in mine.
I thought the opposite.
Okay, now here's what's going on. Okay, what's being reduced? The charge is being reduced. Okay? Charge, or we can say the oxidation state. Oxidation state is reduced. And that's why we call it reduced. I remember when I learned this in this exact class, not this exact class, but 1210, right? And I was thinking, that doesn't make any sense. And all they would have had to say is what I just said, I think. But, so, from there on out, it's kind of like Victor here, he's saying, oh gosh, well, you just have to remember this nonsense, right? Yes, and I try not to make it that way sometimes. Maybe I don't understand something fully enough, and so we just have to, but sorry. You guys ever hear or see a quote by Einstein that says, if you can't explain something simple enough, you don't understand it well enough? Yeah, sometimes I still have that problem. Okay. So it doesn't have to have oxygen to be an oxidation reduction reaction. So this is where the name comes from, because we dealt with iron for since the beginning of time, or any metals, right? And they oxidize, and so that's where we come up with the name oxidation reduction reaction. Another name we call oxidation reduction, just to simplify it, is redox. So I might write that because it's a lot shorter. Oxidation reduction. So here's another way to remember this, which one is oxidized and which one is reduced. Oil rig. Why? Because oil rigs have a lot to do with chemistry, right? Oh, wait.
I think I.
It's just something to help us remember this. Oxidation is a loss of electrons, and reduction is gaining electrons. But if you're ever asked the question, why is it what does oxidation mean? What does reduction mean? Okay? But the way I like to go about it is which one is reduced in charge or oxidation state? That's the reduction, and the other one is oxidation. Michael?
I like to think about it where it's just like oxygen is oxidizing other stuff, and then vice versa.
Sure. That works really well if we have oxygen in the reaction,
Yeah, and then just remember.
but sometimes we won't. I mean, if it's still straight in your mind, I'm not saying do it like I do it. I'm just saying sometimes it doesn't have oxygen in there. And we'll do some examples to where it doesn't. All right, so in order to know the oxidation reduction, we have to determine the oxidation state, or in other words, oxidation number. So for the most part, it's pretty straightforward. When we deal with covalent compounds, it gets a little shifty, but let's talk about it here. So oxidation numbers. Oxidation state / number. Okay, the first one is if it's just an elemental form. In elemental form, so that's like iron, that's like oxygen, any diatomic molecules or any element, right? And then the oxidation number, I'm going to just say OX number, hashtag, okay? That's going to equal 0. Why? Because it's neutral. It didn't lose or gain any electrons at that point. It's just neutral. Make sense so far? So like in this example up here, we started with an oxidation number of 0 for both of those. Because they're in elemental form. It doesn't have to just be iron and oxygen. Any element by itself or any diatomic molecule, okay? Okay, next one is the oxidation number of a monatomic ion. So for monatomic ions, that's like Fe3 plus, that's like Na plus, that's like S2 minus, and so on, right? Just a single element. That's an ion, monatomic. Then the oxidation number is equal to whatever the charge is of that ion. And we've done this before, so we know how to determine the charge, right? Of an ionic of the ions in an ionic compound. That's basically the oxidation state or oxidation number. So far, we didn't learn anything new except for just what it's called. Okay?
So it could be negative or positive.
Yes. So the oxidation number for O2 minus is -2. The oxidation number for sodium ion is +1.
And what is the oxidation number? Like what's the definition of it?
The oxidation number or oxidation state, it is what happened to it according to its electrons in order for it to be that way. So did it lose electrons? Did it gain electrons? Right? So what happened to the electrons in order for it to become that way? or to be bonded with whatever it's bonded to. Okay, the next one is the sum of the oxidation numbers in a compound is equal to the charge of the compound. Most compounds have a charge of what?
0.
0. So the sum of all the oxidation numbers have to add to 0 for most cases. But when we deal with polyatomic ions, now it's not, right? So whatever the charge is, then the sum has to equal that. Because we need to determine the oxidation number for each element in the compound. So if it has a polyatomic ion in it, well, we have to figure out what they are for each element, not just the whole ion. Good? And this brings us into the last one when dealing with covalent compounds. So for covalent compounds, and this is the hardest part of oxidation number, but it's still not really difficult. We just have to remember a few things. So the oxidation number in covalent compounds, we must follow the exact order and here's the following order. So if it's a covalent compound, we ask ourselves, does it have a hydrogen ion, or does it have a hydrogen atom in it? Not ion, but hydrogen atom in it. And if it does, its oxidation number is +1. Does it make sense why it's +1? Because hydrogen is in group 1, and all of those guys have a +1, right? Okay. Why hydrogen first? King of exceptions, right? So we're going to list it first. Then the next one we check, if it doesn't have hydrogen, does it have fluorine? If it's fluorine, what do you think its oxidation number is? -1, -1, yeah. Because that's what its charge would be. It's not exactly the charge. If we're dealing with a covalent compound, they don't have charges, right? But that's how we determine the oxidation number for an atom. Good? And if it doesn't have either of those, we check to see if it has oxygen. If it has oxygen, its oxidation number is
2-.
-2. And we don't call it 2- here, we just call it -2. Right?
So I have a question.
Yeah.
If it has both, like both any of these.
Then you do whatever one comes first. And then we have to calculate the other one. I'll show you how to do that. Great question. Okay, next, if it doesn't have any of those, then we see, does it have chlorine? And then we do this in order also, but all of these have the same oxidation number of -1. Chlorine, bromine, and iodine. And that's the whole list. We don't have to worry about nitrogen, carbon, or nothing else. So not a ton. So let's think about this for a minute. Never mind. We'll just leave it at that.
So is number 3 for ionic compounds? Just ionic compounds?
No, it's for all of them. So if we have, for example, NO3-, that's a covalent compound. The sum of those oxidation numbers has to be equal to what? -1, because that's the charge of that compound. Yeah.
So you're saying the charge of the polyatomic?
Uh-huh.
Okay.
Yep. Polyatomic ions are covalent, right? Any questions on how to determine the oxidation number or oxidation state for an atom in a compound?
Probably, but can we do examples?
No, we're gonna move on. We don't have time. No. I'm just teasing. Yeah, let's do it. Okay, example 1. We're gonna start easy. Let's say we have silver chloride. What kind of compound is this? Ionic. Therefore, the oxidation numbers are just the charge of that ion. What's the charge of chloride ion?
1 -
-1. So I just write it on top with it and just circle it. That's the way I do it. You could do it however you want. And that means silver has to be what? We kind of already did this when we figured out the charge of a transition metal, right? You can do this if you want, no big deal. Same idea. There's one of them, so that's -1. So that has to be +1. Oh, that means the oxidation number for silver is +1. And they add to be what? 0, because that's the charge of silver chloride.
So we don't have to like determine the charge for like every single atom, like just the whole compound is 0. Like if we already know.
Yes, the whole compound, yeah, you wouldn't have to do this if you see, oh, there's just one of each, right?
So just
-1, this has to be +1, right? Has to be 0. And for ionic compounds, we already knew that, right?
they have to be.
It has to be neutral. But for covalent, that's not how it is, right? That's why we have the covalent rule. Does that make sense? Okay, what about oxygen? What's the oxidation number for oxygen in oxygen gas? Just 0 because it's elemental or diatomic molecule, right? So its oxidation number is 0. Does that make sense to everybody? Okay. And what about iron? Oxidation number is
0.
also 0 because it's all alone. It's just elemental form. Okay. Okay, let's do Fe2O3. Think you can do this? Find the oxidation numbers for iron and for oxygen.
Isn't it 0?
They have to add to be 0. And they're not 0 because it's not a single element.
So it's 3 plus for iron and 2 or.
+3 for iron,
-2.
-2 for oxygen. Yeah. Should I go through that? Here we go. Oh, we've done this before, right? We know oxygen is a main group element, so its charge is always going to be what? -2, so that's the oxidation number for oxygen. Well, -2 times 3, because there's 3 of them, plus whatever it is for iron, I'll just say X times 2 has to equal what? 0, because the charge of iron 3 oxide is neutral. Is this the same thing we did here? -6. This side has to be +6. Divided by 2 has to be +3. So you can write it out this way, or you can use this method. Are we good? Okay, ready to try a covalent compound, or do we have any questions so far? Okay, let's do CO2. So CO2 is a covalent compound. You guys know how to tell the difference between ionic and covalent, right? Something we have to know for the rest of the semester. Make sure we know that. All right. So this is a covalent compound. We have to check which element first, carbon or oxygen? Oxygen, because if we go back to this, we got to check this order, right? There's no hydrogen, so we move on. No fluorine, we move on. Oh, it does have oxygen, therefore its oxidation number must be -2. You follow? And do you like this method?
Are both of the oxygens -2, so -4 overall?
Yes.
Okay.
Just like an ionic compound. So -2 times positive times 2 of them is -4. Since this is neutral, then this side has to be +4. If it wasn't neutral, you couldn't do it this way. You following? So this is +4. Another way to do this, because sometimes it's not neutral, then we just say, okay, we have -2 for the oxygen. There's 2 of them. And we add whatever it is for carbon, and there's only 1 of them, and the charge is whatever it is. In this case, it's 0. So we have x equals, this is -4, so we add 4 to both sides. X equals +4.
And are the only exceptions like the same polyatomic ions we've learned already
Exception of what?
to the neutrality?
Well, the rule is the sum of the oxidation numbers in a compound has to equal the charge of the compound. So yes, if it's a polyatomic ion, the charge is not 0.
But that's like the only
Yep.
exception.
Yep.
So, yeah, okay.
Is oxidation number of carbon always going to be +4? It's not. Most of the time, oxygen will be -2. There are a few cases where it's not. That's why you have to check it in that order. Hydrogen, then fluorine, then oxygen, then chlorine, bromine, iodine.
So what we're trying to say, what we're trying to find is the oxidation number for the whole compound or for just?
No, just for each element
For each element of,
within the compound. Mhm. Should we do one that's a little bit more tricky? Okay, let's do K2SO4. Okay, what kind of compound is this? Ionic, but it also has a component of covalent, right? The polyatomic ion. So what's the oxidation number for, what's the easiest one to find? Potassium is +1. Y'all follow me? Okay. Now, we have 2 more. That means we have to check 1 more before we can solve, right? You can't have an equation with 2 unknowns unless you have 2 equations. Yuck, right? So let's find 1 more. Well, this right here is a covalent compound. So for covalent compounds, we follow that order. It doesn't have a hydrogen, doesn't have a fluorine, but it does have an oxygen. So oxygen's oxidation number is -2 in that case. Now we can figure out what it is for S. Now we can treat this one all by itself and say its charge is -2, because that's what sulfate's charge is. Or we can just treat it as one whole unit and say they have to add to be 0 because that's a neutral compound. What do you want to do?
Can we do it both ways?
Yep. Okay, let's do it all together first. Okay, so this this potassium is +1. but there's two of them, so we're gonna multiply that by 2. Plus, whatever it is for sulfur, I'm gonna just call X. I could call it S. Why'd I call it X? What if we're looking for oxygen? And I put O there, it looks like a 0. And that's why I use X. Okay? There's only one sulfur, so we'll just leave it that way. And oxygen is -2, and we're going to multiply that by 4. You following me how I set that up? Questions? Yeah.
Why does potassium have a +1 charge?
Because it's in group 1. In group 1 ions, this is an ionic compound. And if we go to this rule, for monatomic ions, the oxidation number is equal to its charge. So potassium is an ion in an ionic compound. So its charge is +1. That means its oxidation number is also +1. Make sense? Thanks for asking.
So when you have an ionic compound, do you like find the numbers in each of them separately, and then like you don't have to like worry about, you could like separate them into like 2 different ions and then find the oxidation numbers? Is that always possible?
Well, the only time you need to do that is as a polyatomic ion. If it's a binary ionic compound, then it's just whatever the charges are. We don't have to do any calculation at all, right? Unless it's a transition metal. Okay? Did I answer your question? Okay, good. All right, and so the sum of these has to equal what? 0, because this is a neutral compound. Okay? And so we do the math. This is +2 plus S minus 8 equals 0. We can put the 2 and the 8 together, and we get S minus 6 equals 0. We add 6 to both sides, and the oxidation number for sulfur is +6. We good? Okay, now let's just do it this by itself, the sulfate. Okay. So we know oxidation number for oxygen this is a covalent compound, so we start with oxygen. It's -2. -2 times 4 is -8. Plus whatever it is for sulfur has to equal -2. So we add 8, and we still get what? +6. Which way should you do it? Whatever way you want. Whatever way clicks most. Yeah, none of them click. Well, then get practice and get good at it. Okay. And I'd probably just pick one way and just stick that way all the time. I like to just keep it as one unit, but that's me. And if you don't have your polyatomic ions memorized, then you should probably stick it that way, right? Or just memorize them, or have it on your reference sheet. Yeah.
Did you confirm that we could like print something off and paste it on a reference sheet?
I did not, but guess I'll have to email you that too. I called her and then she never called me back, and it just out of my mind. Sorry. I will do that.
Thank you.
Plan on it. Yeah, it should be okay. But yeah, I will check.
Since there's 2 -2s or 2 negatives up there, and you circled both of them with yellow, what is the S plus -8 equals, where did that -2 come from?
This is the charge
That's from the charge.
of
Okay.
sulfate. Yep. And so that's why it has to equal -2. Anything else? All right. We want to take a little demo break, or?
Yes.
Okay, we did do one already. In fact, maybe not yet. Maybe not yet. Sorry. Got a little ahead of myself. I want to hurry and go to those because that's the fun part. But we'll be patient. Here we go. So we do that so that we can determine which one is the oxidation, which one is the reduction, which one is oxidized, which one is reduced. Okay? So determine component that is oxidized and reduced. Okay, so to do this, we have in fact, let's do the one that we did in class. So we had aluminum as a solid, plus we used hydrochloric acid, so it's aqueous. And this is a single replacement reaction. You guys remember talking about single replacement reaction? Where the one that's all by itself comes over and kicks off since it's a metal, it's going to be a cation. It's going to kick off the cation, and it becomes aluminum with chlorine. What's the chemical formula? AlCl3. Because aluminum has a 3+ charge. Chlorine has a 1- charge. You cross them, simplify, and we're going to get left with hydrogen all by itself. What's the formula for hydrogen all by itself? H2. And that's the gas that we produced and almost killed everybody. Okay. All right, so here is a single replacement reaction. Which also determines if it's a single replacement reaction, it is always going to be an oxidation reduction reaction, always. Okay? All right, so now let's look at determine the oxidation numbers for every atom in every compound. So what's the oxidation number of aluminum? Look at your periodic table. Or maybe you don't have to.
Plus, oh, 0?
0, why? Yeah, I kind of tricked you a little bit there, sorry. It's all by itself, so it's 0. Okay, now we have a compound here. This is ionic. How do we know? Because it's aqueous. Okay, dissociates. What's the oxidation number for hydrogen? Chlorine is? Do we have to calculate it? No, it's just an ionic compound. We just take its charge. This is an ionic compound. So what is it for aluminum now? +3. Chlorine is? Still -1. We can check it, right? -1 times 3 is -3 plus a +3. Yeah, it's 0. But we don't have to if it's a binary ionic compound. It's just whatever the charge is. And what's the oxidation number of hydrogen and hydrogen gas? 0, because it's all alone. Okay? All right. To determine which one is reduced and which one is oxidized, I like to start with which one is reduced. That's the one where the oxidation number is reduced. Which one is reduced?
The one that loses electrons? Or
That confuses me. I like to say the one that is reduced is the one where the oxidation number is reduced. So hydrogen goes from +1 to 0. So that is reduced or reduction. Why? What happens to the electrons? It gains electrons. That's why, but, okay. I just say okay because it lowers in oxidation number. So therefore, if it has a reduction, it has to have an oxidation. Which one is oxidized? Aluminum. Goes from 0 to +3. It lost electrons, right? Oxidation. And if it has an oxidation, it will have a reduction, and if it does, it's an oxidation-reduction reaction, or a redox reaction.
Why is it called oxidation if oxygen doesn't need to be involved?
Okay, so remember that first example I gave you? You have iron, it's oxidized, right? And then we just says, okay, oxidized means what? It lost electrons. And reduction means it gains electrons. So that's what we said to begin with. That's why we called it an oxidation-reduction reaction. And then just says if anything loses electrons, it's oxidation. If it gains electrons, it's reduction. So it's just a name that we give it.
Okay.
Yeah.
So does that mean iron could rust without oxygen present?
No.
Why? Like, if it's being oxidized by something else?
Because rust is Fe2O3. Has to have oxygen. And when silver tarnishes, it has to have oxygen. When copper oxidizes and gets that green stuff, has to have oxygen.
But aluminum doesn't,
Yes, it does.
but it's oxidizing here.
Sure, but it's not turning into aluminum tarnish, whatever you call it for aluminum.
Okay. But it's just the change in charge.
Yep. Yeah.
What's the overall charge for the aluminum, chlorine compound? Is it?
It's 0.
It's 0?
How do you know? If we have a compound right here, and then the charge is supposed to be right there. If there's not a number right there, what's the charge? 0.
I meant the oxidation number.
Well, the oxidation number, they have to add to be what?
0.
0. But for aluminum, it's +3 because its charge is +3.
I think because there's 3 chlorines which are -1, so that's +3, -3 equals 0.
That's right.
Okay.
Yep. All ionic compounds are neutral. Remember that?
Right.
All ionic compounds are neutral. They must be. Okay. Do you want to take a break now? And then we'll, do you have any other questions on your mind?
You said if it's a single replacement reaction, it is a redox reaction.
Yes. Yep, always. Yeah.
I thought covalent compounds were 2 nonmetals.
Oh,
Like
that's
aluminum
right.
and other metal. Okay.
That's right.
So it's a metal and a halogen, which makes it ionic?
Yep.
Okay.
Yep.
My bad.
No, that's always ask.
So like the oxidation number, it has a lot to do with like the atom's charges, essentially.
Yeah.
It feels very similar to when we were balancing charges.
Yeah, it is. For ionic compounds, it's exactly the same. Covalent is where it gets a little different. We have to do it in that order that I gave you. And I don't think this order is on your reference sheet that I give you, so you might want to write that down on your reference sheet. Oh, this isn't going to be on the midterm right now, but for the final.
I think those people must be taking the midterm today or something.
So they can have the weekend.
I checked, we have till next Thursday to
Wait a long time.
Is it Thursday or Wednesday?
Next Thursday.
Oh,
I was
okay.
gonna take it today, but the student center is closed, so I can't take it. And that's why it says we can't take it today.
Oh, they're closed today?
They're closed today.
Oh, are they? Man, they
That's
should have closed the
that's what
whole.
Yeah, when I checked, I was gonna take it today, but it was not there. It was only yesterday and the day before. And
Huh,
then
okay.
next week, Monday, Tuesday, Wednesday, Thursday.
Good thing I had it till Thursday then, huh? Okay, we'll do some more, but are there any questions with that? How to determine which is oxidized, which one is reduced? All right, just in case you have to do this on homework, or I don't believe it's going to be tested, but just in case. So in this reaction, we have aluminum is oxidized and hydrogen is reduced. So let's write a half reaction. Two half reactions. So we have aluminum goes to aluminum 3 plus. What happened? It lost electrons, right? So we're going to put them on which side? The reactant side or product side?
Oh, the reactants.
The product side, and here's why. So we're actually going to gain 3 electrons. Or, sorry, lose 3 electrons. It's kind of like, well, we didn't talk about that yet. So, well, we started with this. We lost 3 electrons, and we end with this. You follow? Questions? You're looking like you're not sure.
So the electrons just floating around in space?
Yes, they're just out there somewhere. Yep.
So
No longer a part of aluminum, so it lost 3. So that's why, yeah, well, for a minute, until hydrogen hooks onto them, right? Or chlorine in this case. Okay, so that's one half reaction, and the other half reaction, if we started with H plus, right? And hydrogen gained the electron, so we write it on the reactant side, and then we get H2, right? If we want to balance it, then it gains 2 electrons. You following? All this is showing is what's happening to the electrons. If you add both of these together, then you get aluminum plus 2 H pluses. You're going to get Al3 plus hydrogen. And you're also going to get plus 2 electrons over here, plus, yeah, I don't think we should do that. It doesn't work out numerically wise. But anyway, what happens is the electrons that it gained or lost, they go away, right? But this is not talking about, anyway. I don't know the other, I don't know a whole big purpose of writing half reactions. So I don't think you have to know it, but that's how you write it if you do. Sorry. Okay, we good? Clear as mud, huh?
Can you explain the hydrogen part again? Like it's a 2 charged hydrogen atoms plus 2 electrons just leaves 2 hydrogen atoms that are
Yeah.
ionic, right?
Yeah.
Okay.
Yep. All right, so that's the half reactions. And again, it was in the notes to make sure you know that stuff, but I don't believe it's on the exam. Anyway, I should have checked a little closer. All right, let's do one more before I do a demonstration. Then, okay, so the next type is a synthesis reaction. Sometimes synthesis reactions are called combination reactions. So we did this demonstration already, that's why I'm not going to do it. We have magnesium with oxygen. What do we get? Can you predict this product? And on the exam, you will have to predict this product. You have two elements combined together to make a compound. That's why we call it combination reaction. What's synthesis mean? To make, right? To synthesize, to make, create. So what are we going to make if we have magnesium and oxygen?
Magnesium oxide.
Magnesium oxide. What's the chemical formula for it? NGO.
It's just MgO.
It's a 2 plus 2 minus, right? Since this is a metal and a non-metal, it's going to make an ionic compound. Okay. And we can see that, what's the oxidation number for magnesium by itself? 0. For oxygen in O2? 0. Magnesium in magnesium oxide? Positive 2. Oxygen is negative 2. So which one is reduced? Oxygen is reduced. And magnesium is oxidized. We good? Do you remember that one when we had the strip of magnesium and we burned it in oxygen? And it had that bright light?
Was it, oh yeah, it was outside.
It was right here.
Is that when you burned the table?
Oh, who, what? Oh, I'm talking about, okay. Yeah, there's some marks for it. All right. Okay. What?
Was the smelly one the hydrogen gas that you choked on?
Yeah, it was this last one. This one right here. Aluminum with hydrochloric acid. Yeah.
Were you okay?
My pride went down a little bit, but that's about it. Okay. We good with synthesis or combination reactions and making predictions? What about predicting a single replacement? We good with that? So this guy just kind of knocks off the other cation, swaps just a single replacement. You get the difference between that and double replacement? Okay. And again, you might hear it as single displacement. I don't like that word. It's not what I learned it by, so I don't use it. But the guy who set up this course uses displacement. Sorry. All right, let's do another one. The next one is a decomposition reaction. What does it mean to decompose?
Separate.
Yeah, it's going to be the exact opposite, right? So the example we're going to do is H2O2 as an no, I shouldn't call that an whatever. Goes into H2O and oxygen gas. So let's do the oxidation numbers before and figure out which one is oxidized, which one is reduced, before we do the demonstration. So this is a covalent or ionic compound? Covalent. So we check which first, hydrogen or oxygen? Hydrogen has an oxidation number of positive 1. Look at your periodic table. It's just basically the charge of it, right? If it was an ionic compound. And there's 2 of those, that's positive 2, plus 2, whatever it is for oxygen, has to equal 0. So what's the charge? What's the oxidation number for oxygen?
-1.
-1. So that's an example where it's not -2. Did you follow that, or do I need to show you again?
You're saying it's just positive 2 minus 2 equals 0. Is that
Yeah.
what you're saying?
Yep. +1 times 2, -1 times 2. You add those together and you get 0.
And is that why we start with the hydrogen first?
Yes.
If we started with
Yep, then we would get something different. Yep, you gotta follow that order. And we only check, if there's only 2 atoms, we only check one of them. Okay? If there happens to be more than 2 atoms, then we gotta check another one. But in this class, we're not dealing with big, huge compounds, so. Okay, for water, check with hydrogen again is +1, +2, so what does oxygen have to be? -2. What is it for oxygen and oxygen gas? 0. Any questions on determining oxidation numbers here?
So we always want it to equal 0 for our products?
If it's a neutral compound,
Okay.
Yeah.
It'll just always be 0.
if it's a neutral compound,
Okay.
So it's not,
yeah.
it's not proatomic, ion, right? If it-
But
if it
yes,
does not
the
have
answer is yes, if it's a neutral compound. So the rule says the sum of the oxidation numbers has to equal the charge of the compound. Most times, the charge is 0. Okay. So which one is reduced? Oxygen is reduced. Which one is oxidized? Oxygen. Oh, this is weird. So in this reaction, oxygen is both reduced and oxidized. Good? So you guys can do this at home if you'd like. You guys ever had elephant toothpaste? Okay. This is just hydrogen peroxide, but it's 35% hydrogen peroxide. So the stuff you buy in the store is what? 3%. So it's not as cool with the 3%. If you want better, then you go to a beauty salon and get 6%. But here we go. And just to make it look cooler, why do you put this in? What are we going to get? Oxygen gas. If we have gas is like, makes what in a chemical reaction? Bubbles. We're just going to make it a little bit cooler. And even cooler. I didn't need that much, but. Alright, so now that's cool. This reaction is going on no matter, is already. Because of the temperature in here, it's still reacting. So you have to have a little bit of heat, a little bit of energy, but it doesn't need a lot of energy to get this reaction to go. This is a catalyst. You guys know what a catalyst is? It's something that speeds up the chemical reaction. It actually lowers the activation energy, so it reacts quicker. This is kind of messy. Can you all see that?
Is it gonna be safe, Messi?
Yeah, I'm not gonna die this time.
Okay.
Alright. So this is a high concentrated potassium iodide solution.
Oh my god.
It's exothermic, we can feel that heat coming off of it. And I can feel water, this moist, but all the bubbles, that's oxygen gas. Kinda cool, I guess.
Oh, I see the heat coming up.
Yeah. I got a little bit of iodine on my hands too. Turned it a little bit yellow. Okay. Any questions on that one? It's not real. You don't really use that for elephants, guys. Just look kind of like toothpaste, and it's big, so elephant must be for elephants, I guess. Okay. All right. Let's go to our last one. Oh, nuts. We have a combustion reaction. And combustion reactions are always carbon-hydrogen compounds burning in oxygen gas, and we will always get the same products. So to predict this one, it's always going to be carbon dioxide and water. When you burn gas, you get carbon dioxide and water. Gas is C8H18. When you burn propane, you get carbon dioxide and water. When you burn wood, it's also a carbon-hydrogen compound, or a carbohydrate. You get carbon dioxide and water. So the example we're going to do is rubbing alcohol, C3H8O, plus oxygen gas. I know this has another oxygen, that's okay. We're going to get carbon dioxide and water. So let's determine the oxidation numbers. Start with this compound here. Ooh, we have 3. Which one should we check first? Hydrogen has an oxidation number of +1. We have to check one more. Which one? Oxygen is -2. Now we figure out what it is for carbon. -1 times, or +1 times 8 is +8. -2 times 1 is -2. Plus 3 times whatever it is for carbon has to equal 0. You following me, or did I go too fast? So we got 3x equals +6 equals 0. So -6 to both sides. You got 3x equals -6. So divide 3. And we get what? -2.
So did we do that because there's no charge on the periodic table to know what it would have been?
We don't deal with charges. This is a covalent compound. We have to follow that order. Hydrogen, fluorine, oxygen, chlorine, bromine, iodine.
But I thought oxygen was -1 if it was a covalent.
It was in this one only so far. That was the only one it was -1. What about this one? It's -2. It's only -1 in that particular compound. You have to figure it out. You got to go in that order. Start with hydrogen. Since we knew hydrogen, it's +1. Then we can figure out what it is for oxygen.
I thought that was one of the rules.
That's for covalent compounds only.
Oh, did you say it's not covalent?
This is covalent.
It's covalent. Like we deal with charges, but it's not.
So for ionic compounds, yeah, it's just the charge.
Right,
It's ionic.
but you said that's covalent and we're not using the -1, which is for covalent?
Well,
That's what I'm confused.
for this one right here, it was -1. This is also covalent. Now it's -2.
Did Did you say C3H8O is covalent?
Yeah,
But then if it's covalent, why isn't the oxygen -1?
because, why, that's a good question. Yeah, why isn't it? It's just not. But how you figure it out is you follow this order. You have to follow this order for covalent compounds.
Oh, are we saying because we had hydrogen first?
We have hydrogen in the compound, so we wrote it down.
But you're looking at the example before and this example.
Oh, no.
Is that right?
No, I was just totally misunderstood. I thought that the oxygen wasn't on this chart. I wrote -1, not -2. That's what
Yeah,
in
so
the
yeah,
example
fix
before
that.
we had-
What?
The example before we had H and O, we just checked the hydrogen first. Oh, we only checked the hydrogen and then
Then we figured out, but in this
We
case,
have 3 atoms.
we have 3 atoms, so we have to know one more thing before we can,
Yeah, so we check the hydrogen and then the oxygen and then the last one we check it.
Yep. Yep, that's it. We good?
I. Oh, yeah, no, we're good. That was my fault.
No, I'm glad we got it cleared up so you don't had that in your notes wrong. So what is it for oxygen in O2? 0, because it's all alone. Now we go to carbon dioxide. We check oxygen first is -2. There's 2 of them, so that's -4. So what does carbon have to be? +4. And then we already did water from last time. You don't have to memorize it. We can just figure it out again. So which one is reduced? Oxygen is reduced. You with me? Goes from 0 to -2. I know there's a -2 over here. Doesn't matter which one, we just got to find one that goes down. Which one is oxidized? Carbon, the one that goes up. Goes from -2 to +4.
What about the other oxygen in the?
Yeah, the other oxygen isn't the one that's reduced. Goes from this 2 to this, right? Yeah.
Oh, is this-
Could I have went to this one instead? Sure. Either way, it's still oxygen's being reduced. Good? All right. Let's do this one. Can anybody tell me what's in here?
Air.
Air. And the part that we are interested in is oxygen. This is, well, it's about 21% oxygen in here. This is rubbing alcohol, 70% isopropyl alcohol, which is C3H8O. Why am I covering it? It evaporates. We know that rubbing alcohol evaporates quickly, right? So why am I doing this? To get it to evaporate more quickly, right? And rubbing alcohol is flammable. I let a little bit out. Come on. Broken. Science is broken today. Pretty cool, right? So why did it squeeze in when I did that?
Because you lit the oxygen.
Yeah, I just burned everything out, pushed it out, so there's almost nothing in here. So the pressure in here is really small. Pressure out here was more than inside, so it sucked in. there's the water. A little bit of alcohol. So that is a combustion reaction. We good?
I just have like one note. When we did that reaction, it felt like when you put like a Mentos in a Coke or something like that. Like,
Kind of like that.
and then it,
Yeah.
what kind of reaction is that? Like when you put like a Mentos.
It's an oxidation reduction reaction. Yep. But I couldn't tell you the chemicals involved. You could look it up. I'm sure AI knows. All right. Any questions on oxidation reduction reactions? Okay, one other, there's two other key terms that I need you to know. And these are just names, guys. Why is it called this? Because somebody called it that and it stuck, okay? So the oxidizing agent what's an agent?
Species or compound.
Or okay, but what about a person?
Real thing.
Secret agent, man. Okay. So it's kind of the person that causes something, right? That doing all the work or whatever. But so like a realtor, like a home agent, or what do they call those? Realtor agent. They call it agent, something agent. What are they called? Anyway, a home agent. Are they the ones living in the home? No, they're causing someone else to live there, right? So the oxidizing agent isn't the one that's oxidized, it's causing the oxidation. So who causes the oxidation? The one that's being reduced.
In the last reaction, CO2, so carbon was the one that got oxidized, but O2 didn't get reduced in that area, in the combination reaction.
So in this one right here?
Yeah.
So, yeah, so which one caused oxidation?
O2.
O2. This one right here caused oxidation. Well, that makes sense because it's oxygen, but it was reduced, therefore it caused this one to oxidize.
Well, then what about H2O? Would hydrogen be the reducing agent, even though
So
it didn't get oxidized?
let's see, the reducing agent is the oxidation, or the compound that gives the oxidation. How do we say that? The compound that produces oxidation. So this one right here, this is the compound that is the reducing agent. It causes oxygen to be reduced.
So it's not specifically the hydrogen over there, it's.
Yeah, it's the compound, right?
It's the reducer.
Because how did it become the compound? Because of the oxidation numbers of everything with it, right? Okay. And so it's just a term, I guess. So you can think of it as the flip-flop, but I don't know. Any questions on oxidation reduction or any type of reactions so far?
Are those three reactions we did so far, I mean, the last three, are those all oxidation reduction?
Yes. Yes. How do we know?
So it's,
We just found the oxidation numbers, and there was a reduction and an oxidation. Should we look at a double replacement reaction and see what that is? So if we have HCl plus NaOH gives us NaCl and H2O.
Can we still not find the oxidation?
Let's try it.
Oxidation number?
Yeah, let's try it. What's the oxidation number for this one? +1, -1. That's an ionic compound. +1, +1, -2. I'm doing this quickly. You following me so far? +1, -1. +1. -2. Which one's reduced? None of them. Which one's oxidized? None of them.
That's why I was asking.
All double replacement reactions will look like this. So should you worry about determining the oxidation number for a double replacement reaction? No, we already know it's not an oxidation reduction reaction. So that's the easiest way to tell.
So first find the number.
If it's not a double replacement reaction, then most likely it's oxidation reduction.
What about the single?
Then you check it. What?
What about the single replacement?
Yeah, it's always oxidation reduction
Oh, yeah.
because it's not a double replacement reaction. That easy enough?
Thank you.
So, double replacement reactions are precipitation or acid base. All the rest are oxidation reduction. There are some cases where you don't have any. It's not an oxidation reduction, it's not an acid base, it's not precipitation. Okay? How would you tell? You find the oxidation numbers and see if it oxidizes, it's going to have a reduction. And if it does, it's oxidation reduction. Yeah.
Does it specifically matter, like, if it's asking us to solve, like, to figure out what's reduced and what's oxidized, do we have to also know exactly what type of redox reaction?
I don't think so, but what you should be able to do is be able to make predictions on a combustion reaction. Make a prediction on a decomposition. This one is probably one I probably won't ask you. That one's going to be a little complex, because how do you know it's going to be water and oxygen? Why not just hydrogen and oxygen, right? So I probably won't ask you that one. But synthesis, most cases you should be able to do. And single replacement you should be able to do. And double replacement you should be able to predict the products. Any questions on any of those?
And then, on the synthesis, because it was ionic, we use the charges?
Yes, and that's really the only time I'll have you predict that.
Okay.
If it's a covalent, yeah, a little bit harder. Any questions on chemical reactions? All right, now let's get into the fun part. The math. More math. Stoichiometry. You guys ever heard of stoichiometry? Yuck. Sounds icky. But we already started it a little bit. You guys know how to convert mass to moles, right? Or mass or moles to particles, or mass to particles, or vice versa. Okay? That's going to be most of the conversion factors we do in stoichiometry. But there's one that really tells us this is stoichiometry. And you won't have to. Stoichiometry is just a method, kind of like dimensional analysis. Okay? It is dimensional analysis. But, so stoichiometry, and this is section 6.15 if you're interested in. Okay? This basically, it's to quantify, to make predictions on how much product will be produced if you know how much reactants, or vice versa. If you know how much product you need, well, how much reactants should you put together? And what do we do with that? If we need to know, if we know we need 25 cookies, what do we look at? Our recipe, right? So our balanced equation. We have to have a balanced equation. So let's start with a simple balanced equation. 2H2 plus O2 gives us 2H2O. Now, we know how to find the conversion factor for grams to moles, right? Molar mass. The conversion factor from moles to particles is just Avogadro's number. And here from the balanced equation, we can come up with more conversion factors. And these conversion factors are to go from moles of one substance to moles of a different substance. And so if we start with 2 grams of hydrogen gas, we can figure out how much water we make with that if we react all of that hydrogen gas with it, okay? So here are the conversion factors. 2 moles for this particular reaction, 2 moles of hydrogen gas to every 1 mole of oxygen gas. Can you figure out how I got that? 2 moles of hydrogen gas for every 1 mole of oxygen gas. If there's no coefficient, it's a 1. You with me? We could also do the flip-flop. 1 mole of oxygen gas to every 2 moles of hydrogen gas, depending on where we start and where we're going. So we still have to do this dimensional analysis so that units cancel, and we're left with the unit that we want. Still doing that. Okay. We can do 2 moles of hydrogen gas to every, how many moles of water?
2.
Yeah, right here. 2 moles of water. And we could do the flip-flop of that. 2 moles of water to every 2 moles of hydrogen gas. We have 2 more we can do. What are they? 1 mole of oxygen gas to, good, 2 moles of water. And we can do the flip-flop of that. 2 moles of water to every 1 mole of oxygen gas. Do I have to memorize these? No, you just need to make sure you have a true balanced equation. Otherwise, they're off. Got to have a correctly balanced equation. And basically what this is, I mean, we follow this. This is a recipe, right? We talked about this. Can we double our recipe? Can we cut it in half? Can we have 0.236 of it? Sure. And we use dimensional analysis to figure out how much of each component we need and how much product we're going to get. Kind of like if we want to change our recipe. Normally we just double or triple and make it simple, right? It's not always simple in chemistry. We start with an icky yucky number like 0.236 grams and not moles, right? And then we have to convert it. But it's not too hard.
Why did we say moles, not atoms? One atom of oxygen.
Good. Because if we said atoms, then what would we have to worry about? 6.022 times 10 to the 20. You want to do that?
No.
No, Okay, we don't have to use that ever again. Now that we know it's the same for every atom, every substance, we don't have to use it. We just use moles. That's why we use moles. And that's really why we don't have a device that measures moles, right? It's just so that we can convert theoretically. Does that mean it's not real? No, it means in the lab we make mistakes, right? You ever have a perfect lab? Never, right? There's always going to be error. So this is, we go through stoichiometry to make predictions, and that prediction is in case of zero error. This is what we should get. So if we want to get better results, then better watch how we measure things. And when we're collecting our stuff, better collect it better, right? Or so that we get better results. But there's always going to be some source of error. Does that make sense why we do this, guys? All right. So let's do some examples here. It's done. In fact, before I do that, let me give you the mole roadmap. I kind of started the mole roadmap for you guys, right? So if we have grams of A, and what does A stand for? Maybe our first substance, right? And we can go to moles of that same substance. Oops. And then we can go from moles to particles. Representative particles. We talked about this, yeah? And how do we go from grams to moles? What's the conversion factor? Molar mass. And depending on if we're starting from grams or moles, we flip our molar mass, right? We good with that? What do we do from moles to particles or particles to moles? Avogadro's number. So we already know this. Now, if we want to go from moles of one substance to moles of a different substance, so let's say moles of B, then what we use here is our mole to mole ratio. And where do we find this? On the balanced equation. And that's the conversion factors I just barely showed you with the coefficients. Are we okay? Good so far? Then we can go from moles of substance B to grams of substance B, or moles of substance B to particles of substance B. And how do we do that? Same thing, molar mass or Avogadro's number. So basically this map will tell us where we are and how we get where we're going. And that's basically stoichiometry. Not too bad, right? Sounds ickier. Okay. So let's do a few examples. And we won't finish this today, but we'll kind of go through the main part and then we'll go a little bit deeper next time. Sound good? So hopefully everybody that's not here watches this. I'm telling you guys, right? Okay. All right, here we go. Y'all have this? You want to take a picture of that?
So the really important part is the mole to mole ratio.
Yeah, that's the part we go from one substance to a different substance. They're all important,
Right.
but it just kind of tells us how to get where we're going.
So like we have moles of A. Say like we have grams of gold, we change it to moles of gold, and then we could go from moles of gold to like moles of silver.
Yeah, and then moles of silver to grams of silver, yeah.
Okay, cool.
Yep. According to the chemical reactions, we have to have a balanced chemical reaction in order to do this. If we don't, then all of our work is for naught, okay? All right, let's do an example. If we have 2Al plus 3I2. And don't expect these equations to be balanced for you. You should know how to do that. So can you predict the product here? You should be able to. So somebody tell me what the product is. In fact, what kind of reaction is this?
Ionic.
Okay, it's going to form an ionic compound, but what kind of reaction is this?
Synthesis.
Synthesis reaction or combination reaction, right? Or oxidation reduction reaction. So what's the product we're going to form?
ALI.
ALI3.
Aluminum iodide.
Aluminum is a 3 plus ion.
Yeah.
Iodine is a 1 minus ion. You cross the charge. We still got to do that for ionic compounds, right? Okay. All right. And there should be a 2 right there. Okay, let's say that we start with 0.429 moles of aluminum. I want to know how many moles of iodine are needed to completely react with 0.429 moles of aluminum. So where do we start? In fact, let's go to our mole roadmap. Where are we on this map?
From mole A to mole B.
Yeah. We start at mole A, we can call that moles of aluminum, right? And we want to go to moles of something else, in this case, iodine. Do you see how you can use this? And how do we get there? Our mole-to-mole ratio from our balanced equation. Okay? So we're going to start with what we know. 0.429 moles of aluminum. Now, ladies and gentlemen, it's going to be to your advantage, I think I already told you this, to be organized and write all your units down. That way when you know they cross and cancel, and then you know the unit that you have is correct. Always do this. Okay. So what's the mole-to-mole ratio? What goes on bottom?
Mole of aluminum.
How many moles of aluminum? 2 moles of aluminum. And what goes on top? 3 moles of iodine. Yeah, that's it. Moles of aluminum go away. This tells us we're doing it right. We're left with what we're looking for. We nailed it. So now we just multiply and divide. We're going to get 0.644 moles of I2.
So
Yeah.
importantly, we always want to take the ratios from the reactant side.
Our balanced equation.
Because,
No, whatever one we're going to.
well, because wouldn't we have 6 iodines
Mm-mm.
on the right side?
No,
2 times I3.
Nope. Nope. We have 6 iodine atoms. Do we care about atoms? No, we don't. We're wondering how much I2. We don't want to know how much I we need. How much I2 do we need? Does that make sense? Yeah, if we did want to know how much iodine atom, then yeah, we would. We still wouldn't call it 6 though. Whenever we're going from moles of one substance to moles of another substance, the only thing we use are the coefficients of our balanced equation. That is the only time we use our coefficients. That is why we balance our equations. Good? Okay, thanks for asking. That's a great question. Okay. So let's do another one. Unless you have any questions on that one. Good? So let's say we have propane, C3H8, burning in oxygen. Can anybody tell me what products I get? You need to be able to do this. Yeah, this is a combustion reaction, so what are my products?
Carbon dioxide.
Carbon dioxide and water every time.
Also, every time we have to have water in combustion reaction?
Anytime we have a combustion reaction, we will get carbon dioxide and water
Oh,
every single time.
Okay.
So this one's the easiest if you can recognize that it's a combustion reaction. Yeah,
Combustion reaction always be like.
carbon,
Carbon and a hydrogen.
carbohydrate
Carbohydrate.
burns in oxygen. We're gonna always get carbon dioxide and water.
That
Yep.
makes more sense then.
Yep.
Thank you.
Okay, and let's make sure we have it balanced. And I'll just do it for you so that we can save a little bit of time, but we need to be able to do this. Okay, now let's say if I start with 0.75 moles of propane, I want to know how many grams of carbon dioxide is formed if we react all of the 0.75 moles of propane. How many grams of carbon dioxide is formed? So where do we begin? With what we're given, right? C3H8. And if it's a huge compound, still write it out. It's going to be to your advantage. And, well, let's see. Where are we on this mole roadmap?
So first we want to find moles of.
We start with moles of A. And where are we going?
Then we convert from moles to grams.
Grams of B in the end, right?
Mhm.
So we got to go to moles of B first, and then grams of B. How many conversions is that? 2. It's just 2. Okay? So what's the mole to mole conversion from propane to what?
So it's 1 propane for 3 CO2.
Yep, we got to go to carbon dioxide. So 1 mole of propane goes on the bottom. 3 moles of carbon dioxide on top. Does everybody follow this? So that goes away. We're not at grams of carbon dioxide, so that means we keep going. We're at moles of carbon dioxide. How do we go to grams? We know this. Molar mass, that's it. Molar mass of carbon dioxide, we figured out, 12.01 plus 2 times 16 is 32. That's a total of 44.01. Where does that go, top or bottom? Top, 44.01 grams of carbon dioxide to 1 mole of carbon dioxide. Moles of carbon dioxide go away, we're left with grams, that's what we're looking for. Tells us we can stop converting.
99 grams.
And yeah, 99 grams. And not just 99 grams, but 99 grams of carbon dioxide, right? All the units out, always.
Can you, I'm just getting confused because of like math. How come we're not multiplying by 3 for our CO2 molar mass? 'Cause there's 3 compounds.
We are.
Oh, we already- 'cause we already have it.
0.75 multiply 3 multiply 44.1. Yeah,
I
that's,
see, yeah, sorry, I separated it.
yep,
That makes sense.
that's exactly what we do.
Okay.
And we don't have to worry about the ones. If you want, you can type it in your calculator, just divide 1, right? Doesn't do anything. Making sense?
So we find the molar mass of like CO2.
Uh-huh.
We don't worry about the 3 because we already listed down. Like,
That's right.
we don't worry
When do we use the coefficients? The mole to mole ratio only. That's the only time we ever use those. Good?
So just use, yeah, so just
Yes.
the molar.
Because do we have 3 moles of this? No, we don't. We don't. Like if you was making making cookies, if it calls for a cup of sugar and you're going to cut it in half, are you going to multiply it by 1? Oh, that's a bad example. If it calls for 2 cups of sugar and we're only doing half a recipe, are we gonna multiply it by 2? No, we're not. We're not gonna even use that, right? So the only time we use those coefficients is when we're going from moles of one substance to moles of another substance. That's it. Okay, one more example, and then we'll call it a day. So if we have N2 plus 3H2 gives us 2NH3. Let's say we have 21 grams, let's call it 21.0 grams for our sig figs to work better. And this is in excess, meaning we have more than enough. We want to know how many grams of ammonia will we make. So if we follow our mole roadmap, where do we start? Grams of A, and we want grams of a different substance. So we follow this path. How many conversion factors? 3, that's it. So we did 1 for the first one, that was the simplest, mole to mole. Then we did 2, moles to grams. Now we're going from grams to grams. This is our most complex so far. So we start with 21 grams of N2, and we convert grams into what? Moles. Always go to moles. Okay, so the molar mass of N2 is 28.02 grams. Y'all with me? To 1 mole of N2. Do you have to memorize these atomic masses, guys? No. So use your periodic table and calculate it. Make sure we have that. Okay, we have moles of N2. We want to go to NH3, so let's use the mole to mole ratio.
1 mole N2, 2 mole.
Where does 1 mole of N2 go? On top or bottom? On bottom, so it cancels. To how many moles of NH3? 2 moles of NH3 because of this guy right there. Moles of N2 go away. We need grams of NH3, so we keep going. Molar mass of NH3 is 14.01 plus 1.016. No, 2.016.
3.016.
Oh, there's 3 of them.
Or 3.024.
2.4.
Yeah.
Oh, I made a lot of mistakes there. Okay. I was looking at that and I missed the little curve on that 3. So that is 17.03-ish grams of NH3 to 1 mole of NH3. Everything cancels beautifully except for what we're looking for. Tells us we're done. And we get 25.5 grams of NH3. How are we feeling? Not too bad? It really isn't that difficult. What makes it hard is because it's new. So practice it.
It's not really difficult.
It's not. Okay, we will start on limiting reactants next time. Okay, thank you very much. Have a fantastic weekend. Anybody going somewhere?